It's my great pleasure to introduce today's speaker, Professor Michael Overton from Courant Institute at the NYU. Professor Overton got his PhD in computer science from Stanford University, and he's the chairman of the computer science at the Courant Institute, which is where I got my PhD, and so I know Michael when I was a student there, and also Professor Xiang Yang, also from, yeah, and he's a classmate of our president, Tony Chen. Professor Overton's research interest includes interface of optimization and linear algebra, especially non-smooth optimization problems involve eigenvalues, pseudo-spectral, stability, and robust control. He's a fellow of the SIME and on the editorial board of many leading journals. So we are very happy that he's visiting us today and to give a talk on non-smooth, non-convex optimization.
我好開心嚟到好出名嘅香港科技大學。1976年9月，我嚟過香港。嗰陣時，毛澤東死咗。已經37年，我好開心返嚟。講中文太難，我而家開始講英文。Well, I had some good instruction. I learned some Chinese many years ago, and I used to talk actually with my daughter in Cantonese when she was little. So that's my background. But I really haven't been back to Hong Kong since 1976. And so I hadn't been hearing too much Cantonese in the last 20 years or so. But just being in Hong Kong made me really want to learn Chinese a little better. So I had several good instructors on my little introduction. One was Raymond Chan. One was Su Cheng Choi. But the best one of all was the taxi driver on the way here. So the problem is to find a vector x that locally minimizes f, where f is a function on Rn, real valued. It's continuous. It's not differentiable everywhere. In particular, it's often not differentiable at local minimizers. And it's not convex. There's been a lot of work done in the last 10 to 15, 20 years even on convex optimization, a lot of special methods, but not so much on the non-convex case. And here we're interested in the case that's not only not convex, but not smooth. And what I mean particularly, often not differential. By smooth, I mean essentially continuously differentiable. It's not, the functions we're interested in are not going to be differentiable local minimizers typically. But usually we will assume that at least they're locally Lipschitz. There's a lot of interesting applications, especially in control. So the Clark subdifferential is the primary theoretical tool for non-smooth optimization. It was introduced by Clark a long time ago now. I guess that's 40 years. And he actually used the term generalized gradient, but often people say subdifferential to tie it in with the ordinary convex subdifferential. We're going to assume that f is locally Lipschitz to define this object. And it's defined as the convex hull of limits of gradients. Specifically, that's the formula there. Okay. And so ZR here is going to have to be a point where the function is defined, the gradient is defined. So that's a point in this set. Now, because the function is locally Lipschitz, that's almost everywhere. Okay. And the Clark subdifferential is the convex hull of all the limits that you can get of gradients. You take sequences approaching this particular point x, and we consider we consider the limits of those gradients. And then we take the convex hull. So regularity is an essential term or concept that was introduced by Clark way back then. And why? Because we need chain rules, right? That's why do we use calculus? One of the reasons is that chain rules are incredibly useful. And if we want to use a chain rule for non-smooth analysis, we need to make some kind of regularity assumption. And here's the Clark regularity assumption. Now, a key point here is that it generalizes both smoothness, continuous differentiability, and convexity. So in other words, if a function is convex but non-smooth, then it's regular. If it's smooth but non-convex, it's also regular. So if f is locally Lipschitz and directionally differentiable, which is usually the case in the kinds of things that we're interested in, then we say that f is regular at the point x if for any fixed direction the ordinary directional derivative is upper semi-continuous. So you can only jump up, you can't jump down when you go in these directions d. And if the function is regular at x, then 0 being in the subdifferential is equivalent to the directional derivative being non-negative in every direction. So that's pretty much a first-order optimality condition. That is what it is, in fact. And if you have 0 in the interior of this subdifferential, that's the case if and only if the directional derivative is positive in all non-zero directions. And that really is an optimality condition. You have to go up no matter what direction you go in. So for example, I mean the absolute value function, which is convex, satisfies these conditions because when you move away from 0, you're going up, okay, not down. But the negative absolute value would not be Clark regular. Although it does have the same, the subdifferential of the absolute value function is the interval from -1 to 1, and that's also true for the negative absolute value function. But the second one is not regular. Now, Adrian Lewis introduced a nice concept called partial smoothness, which extends regularity. So a regular function is said to be partially smooth or partly smooth with respect to a manifold containing the point x if, first of all, its restriction to the manifold is twice continuously differentiable near the point. Secondly, the subdifferential is continuous on the manifold near the point, subdifferential being this set-valued set, the convex hull of the gradient limits. And this is a little hard to take in. The subspace parallel to the affine hull of the subdifferential is exactly the normal space to the manifold of the point. That sounds like a bit of a mouthful, but I'll show you a simple example in a second. But if so, then we call this space of parallel, subspace parallel to the affine hull of the subdifferential, we call that the V space, and its orthogonal complement we call the U space. So here is an example of about the simplest regular function, or anyway, almost the simplest regular function that's not convex. And the formula is on the next slide here. Okay, so it's a sum of two terms. One is an absolute value term, and one is a quadratic term. And so you see that there's this valley along the bottom here where the function is smooth, and it's essentially smooth in every direction except crossing over that valley. And the minimizer of this particular function, you can see in a second when I go back to the formula, is actually 1, 1. Okay. So on that manifold, namely this quadratic formula here where this absolute value term is 0, okay, on that manifold, clearly the function is smooth. In fact, it's quadratic. And the subdifferential, what is it? Well, it turns out, so you see on the manifold, you could get two different gradients, going back again to the picture. So at a point which is at the bottom here on the manifold, if you approach from one side, you'll get one gradient. If you approach from the other side, you'll get the other gradient. And so the convex hull of those two things would be the subdifferential. And so that happens to be the formula in this case. And the only minimizer in this case is 1, 1. And at that point, those two gradients are lined up in opposite directions. They're equal. They're the negative of each other, in fact. And so that means that 0 is in the convex hull. Okay. And that's the first order optimality condition that I mentioned a moment ago. And the codimension of that manifold is just 1. It's the dimension of that parallel subspace to the affine hull of that subdifferential. Okay, so that's just a number. That's just 1. And again, you can see that from the picture. It's just that one direction, although it's curved. So more on partial smoothness. It arises in a wide variety of practical settings, including many problems in control, which are what motivated a lot of this. The mathematical properties defining the manifold can vary quite a lot. If the function is partly smooth and convex, then the V space and the U space, remember those were defined in terms of the subdifferential. One is the affine hull of the subdifferential, the other is the orthogonal complement. They coincide with other objects that were introduced by these guys back in the 90s. But these two concepts are different. Neither one is implied by the other. And key point, there's a calculus with a chain rule. Now, what are we going to use for algorithms to locally minimize such a function? So the rules of the game are as follows. We're not going to require the user to provide information about the structure of the function. And in particular, we don't want the user to have to provide information about subgradients or subdifferential formulas. The subgradients are the entries in the subdifferential, the elements of the subdifferential. Because the user might not really know, or it might be quite complicated, we don't want the user to have to provide something about partial smoothness or information about how to smooth the function. Those things are really all just things that we're going to use as theoretical tools, not as computational tools. So instead, what we're going to assume is that given the point x, a user-provided routine returns both the function and the gradient if the function is differentiable at that point. And if it isn't, then it will return something that would be gradient of a nearby point. So for example, if you take something like a max function, max of two things, at the point where they cross, the gradient's not defined, but you could just deliver the gradient from the part on the left or the part on the right. It doesn't really matter. And you'll see why it doesn't matter. That might sound like a very bad thing to do, but it turns out it's not at all. And a key point here is that virtually all continuous functions of interest are differentiable almost everywhere, including all locally Lifshitz functions, and also semi-algebraic functions. And indeed, if you think about it, it's not reasonable anyway in computation and floating point arithmetic to ask whether the function's differentiable or not at a point. I mean, there's roundoff error. It's not a question that really makes sense because it's the question of whether it's differentiable or not at a point, it varies discontinuously. So ideally, what we would like the algorithm to do is generate a sequence converging to Clark stationary points. That means that 0 is in the Clark subdifferential. We'd like to be able to stop it when we're close to that. Okay, that means there's a small vector in the Clark subdifferential. And if f is regular near that point, as I've already mentioned, that's an approximate optimality condition. If f isn't, well, then it isn't, but can't be helped. So here's what happens if you just do the ordinary gradient method. I guess we can't quite read that, but it doesn't really matter. It says steepest descent on this function. And if we start from this point, steepest descent takes you in that direction, line search takes you to there, steepest descent takes you back this way, line search takes you to here, here, and it just jams at this point on the manifold where the function's non-smooth. So this is very typical that steepest descent jams on very simple examples, actually, even simpler than this. And it's been known for decades that that may happen, so you have to do something else. So what should you do? Well, the classical method is to use bundle methods. That requires the user to provide a subgradient, which could be a gradient at differential points, and either way it's an element of the subdifferential. Collect a bundle of these things and compute a search direction by solving a quadratic program defined by the bundle. And there's a lot of good work on these methods, but they're quite complicated, especially in the non-convex case, because you have to sort of decide, how long do you keep these guys around, because it's not like convex optimization where every subgradient gives you some kind of global lower bound. So a very simple alternative is a method that we introduced quite a while ago now called gradient sampling. It's computationally intensive, but what I really like about it is it's a very simple method, and it's got a nice simple convergence theory. And this was introduced by me with Adrian Lewis and Jim Burke, and then the convergence theory was improved just a little bit by Kiviel. So here's the algorithm, very simple idea. You fix the sampling radius, which I'm going to call epsilon. You initialize the point x, and we repeat as follows. We're going to get a set of gradients of the function evaluated at the current point and at points near x, which I'll get just by generating a bunch of perturbed points near x. The sampling is controlled by epsilon, so how far away do we go? Look for the smallest vector in the convex hull of those gradients, okay? And then do a line search in that direction, the negative of that. And then the line search had better satisfy this kind of Armijo reduction condition, if d is not 0, of course. If d is 0, then you're done. Well, you're done at this level of sampling. Now, what happens here is that it starts off just like steepest ascent because the bundle of gradients look just like the gradient of the point. But when you start getting near the point of discontinuity, you get some gradients that are going downhill in this direction, some negative gradients that are going downhill in this direction. And so the convex hull, there's small vectors in the convex hull that go in this direction down here. And so you just steadily progress down here and you get to here. At this point, you've got one negative gradient that looks like this, one that looks like this, one that looks like this maybe, and 0 is in the convex hull. And so then you stop. But you're not done because this is still a rather high sampling radius. And so now what you do is you do an adaptive, well, not exactly adaptive. You keep on going. You reduce the sampling radius by a fixed factor and then just repeat. Okay? And that has a really nice convergence theory. Let xk denote the iterates, and suppose the function's locally Lipschitz, continuously differentiable on an open, dense subset of its domain. And suppose the number of gradients sampled near each iterate is greater than the problem dimension. Now, that's really the weakness of the method, because that's a lot if there's many variables. And then the line search is going to use the sufficient decrease condition that I mentioned a minute ago, saying that the function's actually not just decreased, but decreased by a sufficient amount. Then with probability 1, and I have to say probability 1 because it could be that you could just generate a point where the function's not differentiable, and then the method would just break down at that point. But that's not going to happen with probability 1 if you start with randomly generated information. And we proved that. So in that case, either the function value goes off to minus infinity, so it's unbounded below, or every cluster point of the sequence is Clark stationary. Of course, there might not be a unique minimizer, but every cluster point might jump around, but every limit point is in fact Clark stationary. 0 is in the sub differential. It's kind of amazing that we can do that, even though we never, we have a very simple rule for reducing the sampling radius. We just keep on saying, well, as soon as the rule there for the algorithm is as soon as d is 0, or actually what we have to put is that the norm d is less than a tolerance. And this tolerance is also updated dynamically, I think. I didn't put that into the algorithm. That also has to be reduced. I forget why I didn't put that in, but anyway. So it's a very simple algorithm, and it has this very nice convergence property. And this version I presented is a somewhat improved version by Kiviel. Well, that method is nice and simple, but it's computationally really expensive. Okay, so here's another method called BFGS. Now, any of you who have taken, or in some cases even taught, an optimization course in nonlinear optimization know about quasi-Newton methods. And this is the most famous of the quasi-Newton methods. It stands for Broyden, Fletcher, Goldfarb, and Shano. And here's what the method is. It's updating an approximation to an inverse Hessian matrix. Okay, so if HK was just the second derivative, this would just be Newton's method. Okay, but it's quasi-Newton because you don't plug in the second derivative there. You update it according to these formulas here, and there they are. And that turns out, although it looks like this is a rank 3 update to HK, it's actually a rank 2 update. Turns out this is a well-known fact. And the cost of computing this inverse Hessian approximation is only O of n squared, whereas Newton's method is O of n cubed. Now, O of n squared, of course, is still a lot, and it's getting worse and worse every year when people are talking about millions of variables or billions of variables or whatever. So, you know, this is still a very small-scale method on that scale. But nonetheless, it's a good method for non-smooth, non-convex optimization where you don't have so many alternatives. So this HK models the inverse of the Hessian of the function, and it was introduced for smooth functions. Now, even in the non-convex case, its behavior is not very well understood. And in fact, there are counterexamples to convergence, but they're totally cooked up counterexamples. And for example, they don't apply if you assume the function has some nice property like semi-algebraic as well as smooth, or analytic even. So in the non-smooth case, why on earth would you do such a thing? Well, what happens is that BFGS builds a very ill-conditioned quadratic model of the function. It typically runs until the condition number is machine precision, 1 over machine precision, before breaking down. I was astounded when I first saw this behavior. I thought, well, maybe to the square root of the machine precision. No, all the way to machine precision. The search direction is well scaled in the limit. What that means is that the line search is not expensive. You might have to take 1, 2, 3, 4 evaluations, but it won't get more and more every iteration the way steepest descent would. The step lengths are not 1 in the limit, though, as they would be in the smooth case. That's one of the nice things about quasi-Newton methods in the smooth case. According to the Dennis-Morey theory, you eventually can take steps of 1 and you get superlinear convergence. That's not going to happen in the non-smooth case. So what we do see, though, is linear convergence to local minimizers. It's essential to use the so-called weak Wolfe line search. Now, there's a function. Now, depending on how close you're sitting to the front, it might look smooth or non-smooth here. Now, if it was really non-smooth, if it was the absolute value function, then what line searches do typically is you start with an initial step and then double or bisect until some conditions are satisfied. Now, both of these weak and strong Wolfe methods, they both require sufficient decrease of the function value. That is, if you start here, then the scale at the bottom doesn't really mean anything. This should really be 0 over here. Then the sufficient decrease says that you're not allowed to go over here. Okay, but anywhere in between would be fine. But strong Wolfe says you also need sufficient reduction in the absolute value of the directional derivative. Well, if this is really the absolute value function, you can't reduce the directional derivative in absolute value. It's impossible. So then it's just going to break down immediately. And so it's really essential to use weak Wolfe. And for example, in the famous limited memory BFGS code of Nosadal and others, now I'm not talking about limited memory here, I'm talking about full BFGS, but in their well-known LBFGS code they might well have used, they do in fact require strong Wolfe, so that's not suitable for non-smooth optimization. So let's look at some simple examples. By the way, are there any questions? I've been talking rather fast, so I'm happy to take questions here, especially while I have some water. Okay. Well, can't imagine a more simpler function than this. It's non-smooth, but it's convex. It only has 1 variable. The BFGS update reduces to this because it's just a secant method in 1 dimension. So the top there is a difference of the function values, and the bottom is a difference of the gradients, because you're always going to be crossing over from one side of the absolute value to the other to get reduction and to satisfy the weak Wolfe condition. And so 1 is 1 and 1 is minus 1. So that's why you have 2 here. It's a difference of 1 and minus 1. But the behavior of the successive line search is actually surprisingly complex. The key point, though, is that the initial step is well scaled in the limit, as I already mentioned. Now, for steepest descent on the absolute value, I mean, you'll get there eventually, but the closer you get to the minimizer, 0, since you're taking a step of plus or minus 1, the closer you get, the more function evaluations you're going to have to do in the line search. That's not the case for BFGS. So here's a theorem that explains how BFGS works for the absolute value with n equals 1. Now, it's sort of embarrassing to present results for n equals 1 when, the next speaker will probably be talking about n equals 1,000,000 or a billion or something. But anyway, this is what we can do for BFGS. There's a binary expansion here, which is sort of not a very well-known binary expansion of any real number. You can always sum it, you can call this an alternating binary expansion because of the -1 to the power there. So let's look at an example to understand what this means. So if you take number 4/7, that's 1 minus a half. Now if I put plus a quarter, that's not going to work. I'm going to put, the coefficient of a quarter is going to be 0. So I'm going to put plus 1/8, then minus 1/16, and so on. So that's the expansion for 4/7. Then it turns out that BFGS on the absolute value, starting at that point 4/7, or any point x0, with the initial Hessian approximation as 1, generates exactly the partial sums in this expansion. So x0 is exactly this, it's 4/7. x1, I eliminate the first term. So I've got rid of the 1 now, and it's the sum of this infinite sum. And x2 is this infinite sum, and so on. So clearly this is going to converge to 0 because the infinite sums are getting further and further out. Now what about the rate of convergence? For the absolute value, the function trial values, how do they look? Well, it turns out that they converge to 0 with R linear rate a half. And again, if you've studied any optimization theory, you know that R linear means somehow that it's not exactly by a reduction of a half by every time, but it's at least as good as some sequence. It's bounded, the areas are bounded below by a sequence that is converging by a factor of a half each time. That's Q linear. But even for this incredibly simple function, it's not so trivial. And in particular, we can't extend that to more complicated functions, even with n equals 1, let alone n equals 2. Well, now for n equals 2, I'm going to present the following result. Let's take the 2 norm, very simple function again, square root of the sum of the squares. We're going to do BFGS, but now because the inexact line search is very complicated to analyze, even though it's a very simple method. So I'm just going to look at the exact search, an exact line search. So we're just looking at a quadratic cone and doing BFGS and taking an exact line search. Now normally you wouldn't want to do that for non-smooth functions because you'll end up crossing a discontinuity, and that would be very bad because then you're stuck there and the function's not differentiable. But for the ordinary quadratic cone, the only point that's non-differentiable is the origin. And so when you do the exact line search, you'll always be at a smooth point. So choose H0 not a multiple of the identity and suppose that xk is non-zero for all k. Then for n equals 2, the iterates spiral into the origin with this ratio. Okay, remember these xk plus 1 is obtained from an exact line search from xk using the BFGS update to get the new direction. And again, we don't know how to extend this even to n greater than 2. But numerical experiments indicate that there's something really going on here. And by the way, it also works for the norm of AX, but that's not really surprising because quasi-Newton methods are known to be, their behavior is independent of scaling like this. So again, this is not the case for this function for steepest descent with an exact line search. So here's how the BFGS with exact line search behaves on the norm function for n equals 2, converges relatively fast to 0, n equals 4, n equals 8, n equals 16. Well, of course, bigger n is, the slower it's converging, not surprising. But again, what's remarkable is the consistency of these convergence rates. Now, I'm just measuring these experimentally, okay, and then doing least squares fittings. And what I find is that, okay, for n equals 2, that's log n equals 1, okay, then the negative, the log of the convergence rate, 1 minus the convergent rate is 1. Okay, let's interpret that. So the log of 1 minus the rate is minus 1. So the rate is a half, which is what I had on the previous slide, right? So now we go up to n equals 4, n equals 8, 16, and so on. And you see, I mean, the rate is getting closer and closer to 1, which is bad. But what's nice is that it's incredibly consistent. I mean, there's something really going on there with BFGS that we don't really understand very well. What about the step lengths? Well, here's what we see when we do these different values of n here. The step length converges in the limit. So for n equals 2, you see the step lengths converge to this value. For n equals 4, they converge to this value. N equals 8, n equals 16. And again, we don't have a proof of that, but it's very clear numerically. What's happening to the function value itself? Well, first of all, it sort of dances around a bit, but eventually it just goes down like this. And this is for n equals 16. And oh yeah, so sorry, I didn't say what this is. So the y-axis here, it's not the function value. It's the eigenvalues of the inverse Hessian approximation. Okay? Now notice that they're all going to 0. Well, why is that? Because this is a cone. Every direction at the origin is non-smooth. Okay? So you can think of the second derivative at the origin in every direction as being infinitely big. And so the inverse Hessian approximation should be infinitely small. Okay? And that's what we see. It's converging to 0. All 16 of the eigenvalues in this case, because n equals 16. Well, here's a somewhat more interesting function. It's the one that I showed you the graph of earlier. It's partly smooth with respect to this particular manifold. And so here's n equals 2, and I'm just starting now at a bunch of randomly generated starting points, so let's just follow one of them. So let's take that one. It goes over steepest, the first point is steep. The first direction is, well, it's either steepest ascent or maybe not if the h0 was selected randomly, I think. So it's not actually steepest ascent there. And then it goes up here, eventually comes down, and anyway, I think this one converges to here. I mean, they all converge to there, but it takes them a while to get there. So the different starting points take different routes, but they all get to this point 1, 1. And here's what the function values look like, again, for now that what I'm varying here is not n equals 2, but the weight of the non-smooth term. So as the weight of the non-smooth term gets larger, you'd think the problem is a little harder. Indeed, it is. Okay? And the function values are going down to 0 nicely, but again, it's linearly convergent. Why? We don't exactly know. Here are the convergence rates. Okay? So when the W is big, the convergence rates are slow. When W is small, then the convergence rates are a half. Now that's kind of interesting because if W was actually 0, then this function would be smooth and the convergence rate would be superlinear, and that means that the stars would have to go down here eventually. But because W is not 0, you're not going to see that, even though it's pretty small. Now this is a beautiful test function introduced by Nesterov. It's a diabolical function. So there's a quadratic term there, and then there's this sum of quadratic terms. Now, what does that mean? Can anybody tell me what does that formula look like? Anybody here tell me what that formula looks like? We have a bunch of numerical analysts in the audience. Look familiar? Well, what about the Chebyshev polynomial? It's a Chebyshev recurrence. So it's a smooth function, this. Smooth. Okay? We start at this particular diabolically chosen starting point. The optimizer is here. That's obvious, right? Because then these terms are all 0. Everything is 0, in fact, in that case. Now, consider the following manifold. This is a smooth function, but we can still define this manifold, namely the ones where these guys are 0. That's the Chebyshev recurrence. Okay? So to move from the starting point to the optimizer along that manifold, the variable xn must trace the graph of the Chebyshev polynomial of degree 2 to the n minus 1. That sounds kind of hard. That looks like this. So BFGS takes 6,700 iterations for n equals 8 and more than 50,000 iterations for n equals 10. And Newton's method is about the same, maybe a little bit faster. Okay? So you see, non-convexity really can mess you up, even though it's a unique minimizer. Now here's a non-smooth variant. So instead of putting in quadratic terms here, I'm just putting in absolute values now. Well, now it's even nastier. It's partly smooth now with respect to that manifold. So it is smooth as long as those guys are 0, obviously. That's the only thing that's left. It's much more difficult. BFGS can do pretty well when n equals 3, but not for n equals 4. Breaks down pretty far from the minimizer. It rapidly approximates the manifold, but it can't track that Chebyshev polynomial of degree 2 to the n minus 1. And we conjecture that the reason is actually rounding error, not failure of the method to converge in exact arithmetic. I think in exact arithmetic it would converge. And in fact, we did some experiments with a master's student on using Sherry Lee's high precision double-double package, and indeed we were able to do much better. So this is the Chebyshev-Rosenbrock function. This is the smooth variant, okay, with n equals 2. Your convergence to there. And the non-smooth, oh, not quite sure why this is appearing again, but anyway. Oh, no, sorry, no, now I remember now. Okay, so this one here, this one here is, we've got absolute values here instead of squares, but there's still a square here, okay? And so the Chebyshev recurrence is still the right one. And so for n equals 2, this is the manifold very similar to the Rosenbrock function. You get convergence to there eventually. That's 10 randomly generated starting points, I think, or maybe 7 for the 7 colors in MATLAB. Well, now this is another variant where I put absolute value there inside as well. Now it's not the Chebyshev recurrence anymore. This makes it more difficult. It's no longer partly smooth because the set on which the function is non-smooth has corners. And okay, the function's not even regular at these corners. And it has 2 to the n minus 1 Clark stationary points, which are not local minimizers. In fact, they have directions of linear descent. But they're exponentially hard to find, though. Using enough starting point, BFGS finds all of these Clark stationary points, because once it gets near them, it can't find the descent directions. It's too difficult. And so here you see this for n equals 2. This is the global minimizer over here at 1, 1, but at 0, 1 here, 0, minus 1, you also have some points converging to 0, minus 1, depending on. Well, this is for n equals 5. So I mentioned there were 2 to the n minus 1 Clark stationary values. So with n equals 5, that means there's 16 of them. If I run BFGS from 1,000 randomly generated starting point, I find all of them. Okay, this is just the sorted final values. And okay, I'm a little more likely to find the global minimizer, but clearly as n goes up, it's going to be more and more difficult to find it. That's for n equals 6, and now there's 32 of them. Well, now I'm going to show you a more interesting example, which really does come from an application. It's minimizing a product of eigenvalues. We're minimizing the log, well, log is just for convenience so that the product doesn't get too big, of the k largest eigenvalues of this Hadamard matrix product. That's just a component-wise matrix product of 2 symmetric matrices. X is the variable, A is fixed, okay? And I'm going to require that X is positive semi-definite and has diagonal entries equal to 1. Okay, now it sort of looks like a correlation matrix problem, and indeed it would be a semi-definite program if we were talking about the sum of the k largest eigenvalues, because that's a convex function. But this is not convex, and in particular, if you talk about the product of all of them, it's the determinant, which is actually concave. Now, I'm going to implement the constraint by substituting v transpose for x, where v is a new variable now, it's square, and I'm going to normalize v so its rows have norm 1. That's the same thing as saying that the diagonal of v transpose has to be 1. So now I eliminated both constraints. And then my parameter vector now is this matrix V written as a vector. So that has length n squared. That product, that eigenvalue product, is now partly smooth in the following sense. Given a matrix Y, define an active set which is the indices such that the ith eigenvalue of Y is the kth eigenvalue of Y. That means that there's this cluster of k eigenvalues there. Sorry, not k. K is the one that we're going to prescribe. Say it's the 10th, for example. But suppose there's some other eigenvalues which are equal to the 10th, say the 8th, 9th, and 11th. Then that set would have 4 entries. Okay. So the eigenvalue product is partly smooth in the sense that if you insist that that multiple eigenvalue cluster remains the same and doesn't split up, then everything is differentiable. Now, what's the codimension of such a set? Well, it's been known for a long time. This really goes back to von Neumann, in fact, 1928. The codimension of that set is m times m plus 1 over 2. And then y minus 1, because I'm not telling you what the value of the eigenvalue is. So if I was specifying the value of the eigenvalue and I insist on multiplicity m, it turns out that's a lot of conditions. M times m plus 1 over 2 of them. In particular, if I want multiplicity n, where n is the dimension, then the matrix has to be a multiple of the identity matrix, right? So there's only 1 degree of freedom. And there wouldn't be any if it has to be it has to be the identity matrix. So if we assume that there's some sort of transversality condition here, then this dimension in the parameter space is going to sort of go through in the chain rule. And that's going to still be the right number of parameters, defining some right number of degrees of restriction in the parameterized space. So now I'm going to show you the results that I get running BFGS with n equals 20. Now n equals 20 means the matrix has size 20, but that means that there are 400 variables in the matrix, okay? And I'm going to start, so n is little n is 400, and I'm going to just, I don't know what the analytic solution is anymore. But I'm just going to run it from 10 different randomly generated starting points. This is just a typical picture. And you run it from 10, and the behavior of BFGS from all 10 randomly generated starting points is pretty much the same. They all converge to about the same optimal value. Now, what is the vertical axis here? It's the difference of it's the difference of f at the at the kth iterate here from the final value, meaning the best final value over all 10 iterations. That's what f opt is. Okay. And so it looks like this one here is converging superlinearly, but that's just an artifact of the fact that I'm subtracting, that this is the one that did the best. And so when I subtract off using that value, of course, that gives an advantage to that particular run, because that particular run is really converging to that point. Now, what happens to the log of the eigenvalue product itself? No, sorry, I mean the eigenvalues of the product. Okay, remember, we're minimizing the eigenvalue product, or the log of the eigenvalue product of this matrix where A is fixed and X is a variable, VV transpose. Okay, there's 400 variables. That's the final value that I found according to the previous slide. That's the value of f op that I subtracted off. Okay, what do the eigenvalues of this product look like? Well, here's how they evolve. Now, the interesting thing here is you get this cluster here. There are 9 eigenvalues that come together here. The 10th one looks like it's coming together, but eventually it splits off. And over here, there are 9. And how can we check that? Let's count the rest. 1, 2, 3, 4, 5, 6. Skip that one. 7, 8. Oh, well, okay. 1, 2, 3, 4, 5, 6. This is the multiple one. 7, 8, 9, 10. Oh, there's one up there. 11. So there's 9 in that cluster. So it has multiplicity 9. Okay. What about the properties of the final Hessian matrix? Okay, well, the condition number of the Hessian, the inverse Hessian matrix, it reaches 10 to the minus 16, or 10 to the plus 16. Okay, which is the inverse of the machine precision. Why? Because there are some directions, namely that manifold for which those 9 eigenvalues stay together, there are some directions along that manifold where things are smooth. And in the other directions, things are non-smooth, okay? And what is the dimension of that manifold? Remember I told you it's m times m plus 1 over 2. So it's 9 times 10 over 2 and then minus 1. That's 44. Well, at that point, eventually BFGS has to break down. I mean, we're using finite precision. There's no reduction in the line search. Let's look at the eigenvalues of the final H, okay? So in the non-smooth direction, I'm going to get these really tiny eigenvalues corresponding to huge second derivatives. And the other eigenvalues are just going to be reasonable. That's the smooth space. Well, what's remarkable is that BFGS is really identifying the partition of this space. It's identifying the partial smoothness. The U and V spaces are really spanned by the eigenvectors of the final H. And in this case, as I said, m equals 9, so that quantity there turns out to be 44. Well, there are the eigenvalues of the Hessian. So there's 400 of them, right? Because n equals 400. And I'm not going to count those here, but it turns out I did count them very carefully. There's 44 of them. And the other 400 minus 44 stay reasonably bounded, okay? and the other 40, these 44 are really going to 0. So it really figured out that that this function is partially smooth with a dimension of v space equal to 44. But more than that, if I look at the eigenvectors corresponding to those eigenvalues, well, for the ones corresponding to the first 44 eigenvalues, like the blue one and the green one, you see, let's see, which ones are those? So the blue one, yeah, the blue one is non-smooth, and the green one is also non-smooth, and then the others are smooth. Okay, the function is really behaving smoothly in this direction. So it's the non-smooth directions that correspond to those first 44 eigenvalues. I may have said that the wrong way around before. Because the dimension of that manifold is 44, the codimension. And so you see those two, the blue and the green, are part of the first 44. So you have this V-shaped behavior here when you look at a plot of the function along that eigenvector, subtracting off this optimal value. Okay, and then these are the smooth directions. Most of them are smooth directions. Okay, well, what about some other problems? So here's a bunch of problems that were in a PhD thesis from Finland. This was a master's student who carried this out. We didn't compare gradient sampling in this case because it's much too slow. So we compared a bunch of other methods. This is a method from the Soviet Union as it was then, back in the 80s. Okay, it's a pretty well-known method. This is just a variant of it on the internet that we found. This is a bundle code that somebody was kind enough to lend us, Sagasta, Zabala, and Hare. This is just limited memory BFGS, because with BFGS, it's going to be too expensive if the number of variables gets more than, say, 1,000, okay, because of n squared. Limited memory BFGS is very fast, but it's kind of a, magical method. Nobody really understands why it works as well as it does. What is it doing? It's just keeping the most recent updates to the BFGS method. So it's a kind of a mysterious method. And then this was the Finnish student's method, where she combined LBFGS and bundle. So what we found, what Anders found, was that these are performance profiles. Now, those of you, probably none of you have seen performance profiles. I guess maybe some of you have. Roland, for instance. Maybe some others too. But I don't want to explain the details, but basically it means you're looking at the information accumulated from a whole bunch of test sets, a whole bunch of test problems in one set. And it's good to be up high here as you go along. So what this right-hand endpoint means that these two methods here solved 75% of the problems eventually before they were terminated. And back here, this means that, this is, let me not try and explain what that part means. But anyway, it's good to be up high, basically. We could look it up. Okay, and this is for some bigger problems with 10,000 variables. And here we found that these were the only two methods we could even run now. Limited memory BFGS without anything else in it, just Nosedel's code, in fact. No, I guess not. No, I think my code or Skoya's code, because we needed to have the other line search. And then there's this is the Finnish one. So we found that ours was a little better. Now, I should say, in fairness, that I recently got an email from a guy called Navon, who's been doing quite a lot of interesting weather prediction problems, which have large non-smooth problems. And he found the opposite. He found that actually LMBM was really actually better than just plain LBFGS. Now, continuing on the theme of large problems, I have another master's student right now who has been modifying Nosedel's code for limited memory BFGS. Now, one reason why that code is so popular is because it implements simple bounds on the variables. So that's very valuable. And he's been modifying that code to use a more appropriate line search for non-smooth optimization, also stopping criterion. And so on non-smooth problems, like non-smooth Rosenbrock functions, for instance, the new code is much, much better than the other code, which wasn't designed for non-smooth problems. The LMBM doesn't allow bounds, I don't believe. This is just another test set, and their BFGS was doing the best. These other methods, these are very strange methods. I don't think there's any good reason to be using those methods. Redist prox maybe, because it's one of the bundle methods, and certainly there's been a lot of work on bundle methods. Well, what's going on here? There's a theoretical challenge here. So here's the challenge. Consider any locally Lipschitz semi-algebraic function. Now that just means it's some kind of reasonable function you can write down with formulas, more or less. Actually, what it technically means is that the graph of the function consists of a finite number of pieces, each of which is defined by a finite number of polynomial inequalities. Initialize x and h randomly. That's the initial inverse Hessian update, initial inverse Hessian. Prove or disprove that with probability 1, BFGS generates an infinite sequence of iterates. Any cluster point of the sequence is Clark stationary. The sequence of function trial values, that is the ones generated by the line search, converge to that cluster value R linearly, and that if F is partly smooth and the sequence of iterates converges to that point, then the limiting null space of H is actually the V space. Okay, in other words, the eigenvalues that are going to 0 are really the ones corresponding to the non-smooth direction. Well, we have no idea how to prove this. Adrian Lewis and I have spent a lot of time thinking about these questions. We got up as far as n equals 2, and that was with an exact line search. But you know, there are a lot of smart people in Hong Kong, so maybe somebody here can solve this problem. Here's some other open questions. What even measures the conditioning of a locally Lipschitz non-smooth optimization problem? We don't even understand that. Condition number is such a well-known thing in numerical analysis. We know, of course, what it means for linear systems. We know what it means for linear programs, although I think there's a bunch of variants, but Renegades is sort of the standard one. We know what it means in lots of contexts. We have no clue what it means in this context. It should somehow depend on the curvature of the manifold, but also on the conditioning of the function restricted to the manifold. And if linear convergence takes place, shouldn't that depend on this condition number? But we don't know what it is anyway. How to decide when to stop? Well, now interestingly, Lamarchal thought about using BFGS for non-smooth functions a long time ago, and it's written as a sort of side remark in one of his very old unpublished papers. And he said, oh yeah, it works pretty well. But he pointed out that there's no way to know when to stop it. Now, certainly looking at the condition number of the H matrix would not be a good idea because that would be O of n cubed computation. But what we can do is we can save the most recent gradients generated by BFGS in a set, call it G. Look at the smallest vector in their convex hull, because if you're getting to a point, if you're sort of getting to a cluster point, there may be a whole bunch of them, okay? A whole bunch of them would, actually, I'm going to require them to be sufficiently close. I didn't say that there. And I'll terminate if that direction, in other words, they're valued at points that are sufficiently close from my current point. Then it's reasonable to terminate. That's like an approximate Clark stationary condition. Now, if D is small, well, I just said that, okay. That's assuming the function's regular, actually. No, this is a Clark stationary condition, but if it's regular, it's an approximate first-order local optimality condition. And if n equals 1, that is, you're only keeping the latest gradient, well, it's just the usual check on the norm of the gradient, okay, which is what you normally use for stopping criterion. Okay, so that's what we could do as a stopping condition. Now, if we don't know what to use for n, we could do an a posteriori check instead, and that's what I'm going to show you on the next slide. Let me skip that. So here's what this means. So this is my, suppose I started the latest point. I think this was for the eigenvalue product problem. Suppose I start at the latest point, just use the latest gradient. Okay, well then the norm of the gradient is big. Okay, when I keep on adding more gradients to the mix, norm of the gradient is up here. This is the distance at which we're evaluating the gradients. So by the time I'm getting over here, I'm looking at the 40 nearest gradients. And by the time I'm over here, I'm looking at the 60 nearest gradients. Okay? Well, at that point, when you include the 60 nearest gradients, all of a sudden, the smallest vector in the convex hull drops to close to the square root of the machine precision. So why around 50 or 60? Because 44, presumably, because 44 is a dimension of that V space. So that's consistent. But again, we can't prove that. So President Chan, I should remind you, you have a meeting. But maybe it's not that important. Okay, so here's a code that we have, hybrid algorithm for non-smooth optimization. Version 2.0, we run BFGS until termination condition on the gradient is satisfied, on the gradient satisfied. Then we switch to gradient sampling. Sometimes it might do a little better, especially for the non-Lipschitz case. But the nicest part of it is that then we have a convergence theorem at that point. Includes the limited memory option, and it's available, so you can free to use it. Now, I'll just quickly tell you about constraint problems. Suppose we have a bunch of constraints that are also non-smooth and non-convex. Well, this is a pretty hard problem. And if I assume only that the function and the constraints are locally Lipschitz and continuously differentiable on their open dense subsets, there's not too many methods out there. I don't really know of any. Tony, great to see you. Thank you so much for the invitation. Okay, so we were able to extend, or really I should say Frank Curtis, who's this very smart guy who was a student of Nosadal and postdoc at NYU a few years ago. Now he's at Lehigh. He was the one who extended the convergence properties to this case. And I think that's really very nice work. I can say that since I just said he did most of the work. I don't think there's any other methods which have convergent theory for that kind of problem class. Of course, it's not very efficient, but it's nice to have something. Here are some applications in control that do I have enough time just for 3 more minutes? Yeah. So just tell you a little bit about this. So consider the following linear time invariant system. This is, I used prime for a time derivative. X dot equals AX plus a control input, okay? But I wanted to design a controller that chooses U to stabilize the system and also optimizes some kind of performance measure. Now, it's known how to do this using a so-called full-order controller that's of order equal to the dimension of the state space, the space in which we have this differential equation, length of X. But that's not very practical in many applications. In fact, engineers really don't like full-order controllers. The math people like it because they know how to solve the Riccati equations and the Lyapunov equations that give you the answer. But the application guys say, but that controller is way too complicated. I have no idea what it's doing. So they would much rather have like a second or third order controller that they understand. And I know I haven't really explained what the order of the controller means, but there isn't really time for that. So there are not very many variables in these problems, but they're hard. And we have a code called HaiFu, which in French for Roland is pronounced Ashifu. It's pronounced, there are no guarantees, but it works pretty well in practice. And there's a user-friendly, flexible interface. Now, I should, again, sort of for full disclosure, I should say there's actually a new code in MATLAB now called HInstruct, which is really a competitor of HaiFu and was to some extent developed as a competitor to HaiFu, which is a lot faster. But of course, those guys have a lot of time to fine-tune things. And I think we had some impact on the design of that thing. So it's built on, our code is built on BFGS and gradient sampling. They use their bundle code. Here are some benchmarks. 13 standard examples from the literature. This was in the American Control Conference from 2008. And then 17 so-called strong stabilization. I won't get into what that means. Anyway, in virtually all cases, HaiFu found controllers with lower order and better H-infinity performance than published results in the literature. Now, I didn't tell you what the H-infinity norm is, but it's a rather complicated thing involving the feedback, how the feedback controller is designed. I could tell you more, but it would take too long. So we're happy to see this used for quite a few different kinds of applications. Aircraft controller for improved gust alleviation, robust controller design for proton exchange membrane fuel cell system, design of power systems, and design of winding systems for elastic web materials. And here's some of our papers. So let me just point out some of the papers. So this is a rather theoretical paper about what happens when you randomly sample gradients. Can you approximate the sub differential? It turns out the answer is yes. This is a method about gradient sampling, and this, well, I mentioned already, it was extended a little bit by Kiviel and simplified a bit. I'm very fond of this paper that I wrote with Adrian Lewis. It took us a long time to get this thing published because the referees were annoyed that there weren't really any theoretical results, you know how referees can be. I felt there was a lot of insight. Anyway, eventually it was accepted for math programming. This one, whoops. This is the one for constraints with Frank Curtis. And this is the limited memory thing by the master's student. And anyway, you can find all this stuff on my website. So that's it. So 多謝你哋嘅注意。
Basically, you still assume there's some local Lipschitz on the especially for the solution point, right? Local Lipschitz.
Well, for the convergence results, yes.
Right.
I mean, we've actually run a lot of other examples which are not locally Lipschitz, especially I'm very fond of these examples like the spectral radius of a matrix which depends on some parameters, which is not locally Lipschitz if you have multiple eigenvalues.
Okay.
And then what happens is that gradient sampling works pretty well even though the convergence theory doesn't apply. BFGS doesn't work as well, but it still, you know, gets close.
Okay.
Does that answer your question?
Yeah, sure. Because some people are working on some non-smooth, non-Lipschitz, and non-convex.
In fact, there was a talk about it yesterday at the conference. Is that person here?
I don't think so.
No. I don't remember where he was from. Do you? Was he from Hong Kong?
I think it's some student
Maybe from Beijing.
Of Xiaojin Chen. I think some student of Xiaojin Chen, the organizer of the conference last year.
Ah, okay. So he's at Hong Kong Polytechnic.
Right.
Yeah. I didn't really get a chance to talk with him, but I went to his talk.
Okay, good.
It was a pretty theoretical talk, though, I think. Yeah. Yeah, Roland.
Yes. So do you think there is some hope that you can handle a generalized to non-smooth functional like the indicator functional of a non-convex set? Yeah.
Well, the indicator functional would be discontinuous, right?
No, I know, but precisely. Yeah. So going beyond.
Right, with the functions discontinuous. I mean, actually, in the code, we do deal with it in the sense that, for example, for the H infinity norm, if the matrix is unstable, then the H infinity norm should really be considered to be plus infinity. So in other words, if there's an eigenvalue in the right half plane, we return the function value plus infinity. Then as long as you don't start there, it's okay, because if the line search takes you there, plus infinity then you reject that value, and you can track back, and eventually you get back to near where a function is differentiable. Now, I guess what you're talking about is suppose the function decreases until suddenly in the limit it jumps up to plus infinity. Actually, we have seen that example too in some applications, because it turns out there's some nasty control problems where exactly that happens, that there's some eigenvalues being pushed to the imaginary axis, but if they cross over, then things jump up to plus infinity. So yes, I think we actually can handle that. The code does handle that. But of course, to prove anything is a different story.
Yeah, another question, especially Germany, Austria, etc. Some group of people are very big about semi-smooth Newton.
That's right.
Can you comment about?
Well, so I didn't used to be very interested in semi-smooth Newton. However, I went to a talk yesterday by Jiawang Ni, really beautiful talk, and he was doing semi-definite programming for a particular application. It has to do with Toeplitz matrices and has to do with finding rank 1 approximations to Toeplitz, not Toeplitz, tensor, rank 1 rank 1 approximations to tensor, like the equivalent, the generalization of the SVD, okay? So it was a really beautiful talk where he was generating some semi-definite programs that were huge, and then he'd solve them using the code of Defeng Sun at National University of Singapore. And that code is super impressive, and it is based on semi-smooth Newton methods. So it looks to me, based on that that's by far the best code out there right now for large-scale semi-definite programming. So I think, I think it works because he's doing Newton's method, and the function's not smooth, but they're able to do it anyway because the function's semi-smooth. But they've only recently, in recent years, sort of figured out how to put all that stuff together, I believe. I'm not sure who the Europeans are, but I would say right now the center of gravity has moved over here. Who are you thinking of? Okay, yeah. Yeah, okay, that makes sense. Yeah. So it started in the West, and now it's better in the Far East. Okay. Other questions?
Let's thank Michael again.